Hello again. In this video, I would like to teach you how do you use the package in R to estimate the population mean and population variance at the same time using GIP sampler. But there is not right by writing a code like I did in the last lab, but using the R JAGS library. If you would like to familiarize yourself or get more information about this package, you can take a copy from this one and paste on your browser or this one. Those are some good resources, but there are many other resources on the internet you can look at. So let's apply the idea or use the package for the same data set we worked with, which is the house prices. So let me upload the data first. The same data again. I will work with price, but you can practice on anything else. I will calculate Y as the house price. And then I graph the histogram again. We did the same thing before, but let's do it again. And then number of values. And now let's set the priors as we have set them before again. Use the prior distribution for the population mean, Jeffreys prior, non-informative prior, mean 0, variance very big value. So mu 0 is 0, sigma 0 square is 1000. And use the open box prior for the population variance, inverse gamma 0.01, 0.01. This one doesn't have much information. It has a little bit information. So it looks like non-informative prior, alpha and beta. And then how do I use JAGS? Before you use JAGS library, you need to take a copy from this one and download the JAGS. So take the copy from this one based on your browser and then download the MCMC JAGS package. And then after that, after you download it, go to R and then install the R JAGS package. You take a copy from this one and run on R. The third step is you need to write library RJAGS. And then in this package, you need to specify two things: the likelihood and the prior distribution. Only these two. You need to give the package the prior distributions and the likelihood or the data distribution. And using the data distribution, the package or the function will change the probability distribution or the data distribution into likelihood, and then it will multiply the likelihood by the prior distributions and then get the posterior distribution on all the other job. So you need to specify only the statistical model as a likelihood and prior, and then the package will do the rest of the work. And then you compile the model and then you create random samples. So let's do it. Let's upload library. And then let's look at the model specification. Let's look at the model specification. This is the model specification or the definition of the model. You give a name for the model, any name, you can change this name. And then between quotation, you write the model, open curly bracket, and then define the likelihood or define the probability distribution, the data distribution actually. And it will be changed to be likely. And then the prior distribution. So for I equal 1 up to n, yi, each yi randomly selected from normal distribution with mean mu and tau square. We are not going to work with sigma square. We will work with 1 divided by sigma square. But I will ask R also to find the random sample from sigma square, is not tau square. I will show you. So the first loop is to define the data distribution, and the function will use this one to find the likelihood. So each y value follows normal distribution with mean mu and tau square. What is y? Y is the data itself, which is the house price, which is the house price. I give a notation y equal, this is the house price. And then let's assign a prior distribution for mu. So mu will follow normal distribution with mean mu 0 and tau 0 square. Tau 0 square is 1 divided by sigma 0 square. And I defined sigma 0 square before. So this is mu 0 and this is tau 0 square. So I use these to define the prior distribution for mu. And tau square is 1 divided by sigma square. Or tau 0 square is 1 divided by sigma 0 square. And then I give a prior distribution for the variance, which is inverse gamma. So if I work with sigma square, I will assign a distribution inverse gamma. But if I work with tau square, I assign gamma distribution with the same alpha and beta. Alpha and beta used in the prior distribution are 0.01, 0.01. So again, if I assign a prior distribution for the variance, it would be inverse gamma. If I assign a prior distribution for the taus, I assign distribution gamma. And then I will ask R to calculate sigma square 1 divided by tau square. So I will randomly select a sample from tau square, and then I will change it to be sigma square. So this is the model. The data distribution, the prior for mu, the prior for tau, and then the relationship between tau and sigma square. So let's have this one. And then I will compile the model to make sure everything is fine, and the function will randomly select initial values. So I gave a name, I save everything under this name, model, and the function is JAGS model. And then I use text connection. I gave the name of the model, the definition of the model that I gave before. And then I will ask for number of chains. Let's ask for 4, change it simultaneously. And I gave the data like y equal y, n equal n, mu 0 equal mu 0, sigma 0 square equal 0, sigma 0 square, alpha equal alpha, beta equal beta. Because this code is a function of those guys. So I gave these values. So let me add this one. It's said initializing model. So everything is fine. But if it gives some error, it means there is some error in the definition or anything else. So now I will draw samples, or I'll ask R to draw samples from each posterior distribution. We have 2 posterior distributions for the 2 parameters, one for mu, one for sigma square. So the first line with the update function draws 10,000 of warm-up samples. Those will be discarded. Those will be removed. And then after that, I will ask to randomly select 20,000, assuming the conversions will happen at 10,000. But I will see if the conversions happen at 10,000 or before 10,000 is fine. But after 10,000, I will come back and change this one. So update the model. And in the warm-up or the per-nan is 10,000. And do not show me the progress. So the progress part is none. This one is because I don't like to give me something like 20% finish, 30% finish, 50% finish. I don't like to see this one, but it's fine if you'd like to remove this one. So let's update. And then use the coda samples function to find a random sample from each posterior distribution. Each one is 20,000 for each chain, but you randomly run 4 for each parameter. So 20 times 4 is 80,000 for each parameter after we remove the first 10,000 from each chain. And I will ask to save the random sample from mu, random sample from sigma square. If I remove this one, it will save only random sample from for the parameter sigma square. But I'm interested in both of them because sometimes you have many parameters, but you are interested in a few of them. So let me run this one. And then let's summarize the samples. I would like to calculate the posterior mean for the population mean, posterior mean for the population variance, the first quartile, second quartile, third quartile, and so on. So let's have some summary. So let's read this summary. It sets the iteration after 10,000, so starting from 10,001 to 30,000, and the number of changes is 4, and the sample size for per change is 20,000. The empirical mean and the standard deviation for each variable, plus the standard error of the mean is this one. The posterior mean of mu is 122.7. The posterior standard deviation is 5.642. And then the posterior mean of the sigma square is this one. The posterior standard deviation is this one. So what is the naive standard error time series standard error? The standard error in general is S divided by square root of n. So it is the standard deviation divided by the square root of the sample. How many values is used to calculate the standard deviation? But the time series is S not divided by the sample size, it divided by the effective sample size. So this is why this one is bigger than this one, because the effective sample size, for sure, it is smaller than the sample size. So because this one take into account the dependency in the sample, but this one doesn't take the dependency within when it estimates. But if this one is very close to this one, it means there is no much dependency. There is no much autocorrelation in the samples. But if this one is completely different from this one, it means there is much autocorrelation in these samples. And this is a naive standard deviation for sigma square. The this is the time series standard error. Naive standard error for the sigma square. A time series the standard error for sigma square. So, and then this is another summary. This is a 2.5 percentile, 25 percentile, 55 percentile. So this is the median of mu, or the posterior median for mu, posterior median for sigma square. This is the lower limit of the 95% credible sub. This is the upper limit of the 95% credible sub. So for mu, the credible sub, 95% credible sub as 111.6 and 133.7. So with 95% probability, the population mean is between these two values. For the population variance with 95% probability, the population variance is between these two values. And this is the posterior median of mu, and this is the posterior median of sigma squared. So now let's see the effective sample size. Effective sample size for mu is 77,746. For sigma is 77,898. The total should be actually 80,000, but because there is some autocorrelation, the effective sample size is smaller. But 77,000 is good. It's very good one. So looks like convergence happened. How do I know convergence happened? Let's plot these samples. Let's plot the trace plots. It takes some time. Keep in your mind, I have 4 changes at the same time. So you have 4 colors for each trace plot. So this is this trace plot of mu. Looks like convergence happened. The 4 samples mixed well. And they are randomly scattered above and below some specific value. The same thing for the trace plot for sigma square. The 4 change mixed well. And this is a graphical representation of the posterior distribution of mu. And here we will have the graphical representation of sigma square, the posterior distribution of sigma square. See, it is a little bit skewed to right because actually sigma square follows inverse gamma. So it is skewed to right. But this one follows normal distribution. This is why it is normally distributed or bell-shaped symmetric. Let's look at the autocorrelation. Because I see the effective sample is very big, it is very close to the sample size. So it looks like there is no much autocorrelation. Let's look at the autocorrelation. See the correlation at the lag 0 is 1, it is always 1, and the other lags the correlation is very almost 0. It means almost there is no autocorrelation. It means every value almost doesn't depend on the previous ones. Every value doesn't depend on the previous ones. Every value I generated, it doesn't depend on the previous ones, which is a very good situation. And also we can check the convergence using the Gell-Mann-Rapin statistic. So let's calculate the Gell-Mann-Rapin plot. So I need to add enter. Let's see, let's wait until we get the Gell-Mann-Rapin plot. It shouldn't take that much time. Looks like my computer is very slow today. I don't know why, but let's wait. Where is Gell-Mann-Rapin plot? So let's hit it again. Oh, this is the Gell-Mann-Rapin plot. See, it is 1.03. This one is close to 1. So it looks like the convergence happened from the very beginning for the first parameter mu, and also 1.015 is very close to 1, so it looks like convergence happened at the very beginning. So I used 1000, and from the 1000 looks like convergence happened, 1000 convergence happened. So I know this one is far away, looks like very far away from 1, but it's not far away from 1. You look at the y-axis, it is 1.03. And this one is almost 1. So 1.05 is fine, 1.1 is fine, but I said start from 10,000 and looks like the convergence happened at 10,000, which is fine. Okay, guys, thank you so much, and see you in another video.